Institute of Engineering and Technology. Today we will discuss few more topics of Fourier series. So let's begin with Fourier series of even and odd function. So firstly we'll discuss what is even function. Let fx be a function defined over a symmetric interval minus L to L. Then the function fx is even if f of minus x is equal to fx for all x. If this interval is given a symmetric interval, right, from minus L to L, then and if f of minus x is equals to fx, then the function will be called even function. So let's discuss about odd function. Let fx be a function defined over a symmetric interval. Again, we need a symmetric interval. So here we have minus L to L interval. And if f of minus x is equal to minus of fx, then we can see that the function fx is odd function. Let's see example. Firstly, f of x is equal to x square. So here we will check whether this function f of x is equal to x square is even or odd. So for that we have to substitute f of minus x. Okay, so here in place of x we will substitute minus x, right? So here you will get minus x whole square, right? So that is x square. So here we have f of minus x is equal to fx. Therefore function fx is equal to x square is known as even function. Next, see the graph of a function fx is equal to x square. Here you can see this is a parabola and also it is symmetric about y-axis. So a even function is always symmetric about y-axis. Let's see one more example, that is f of x is equal to cos x. Again f of minus x, that is cos of minus x, which is cos x. Okay, so again we have f of minus x is equal to f of x. Therefore the function fx is equal to cos x is even function. The graph of function cos x, again you can see this graph is symmetric about y-axis. So the even functions are always symmetric about y-axis. Let's see few more examples. The function fx is equal to x cube. Again same procedure, f of minus x is equal to minus x whole cube. So it will become minus x cube, right? Now x cube is equal to function fx. So here we can write as minus of fx. So here we have f of minus x is equal to minus fx. Therefore the function fx is equal to x cube is odd function. The graph of fx equal to x cube is shown here. Now this graph is symmetric about origin. Okay, as you can see in the graph. Let's see one more example, that is function f of x is equal to sin x. So again substitute f of minus x is equal to sin of minus x, that is minus sin x. Okay, so here again we have minus f of x. So f of minus x is equal to minus fx. Therefore f of x equals to sin x is an odd function. The graph of sin x, again you can see this graph is symmetric about origin. Okay, so for an even function the graph will be symmetric about the y-axis, and for an odd function the graph will be symmetric about origin. So now let's discuss properties of even and odd function. The first property, as we have already discussed, is the graph of an even function is always symmetric about y-axis. Next, the graph of an odd function is symmetric about origin. Next one, the product of two even function is even. For example, multiply x square with cos x. So you will get an even function, right? Next, the product of two odd function is even function. If we multiply x cube with sin x, so x cube sin x will be an even function. Next, the product of even and odd function is odd function. So if we multiply x square with sin x, okay, so x square sin x will be an odd function. Next one, the sum or a difference of two even function is even function, and the sum or a difference of two odd function will be odd function. Let's see few more properties. The first one, if f of x is an even function, then integration minus L to L f of x dx will be equal to 2 times 0 to L f of x dx. You have to remember this as a formula, but you have to remember two things. The first one is function should be even and the interval minus L to L, or a symmetric interval, right? In an symmetric interval, for an even function, if minus L to L f of x dx will be 2 times 0 to L f of x dx. Now what about an odd function? So minus L to L f of x dx will be equal to 0. If function is odd and it is in the interval is symmetric, then the integration will be 0. Okay. Now let's discuss the Fourier series of an even function fx in the interval minus pi to pi. Okay, so here our function is even and we are considering the interval minus pi to pi. So the formula for fx will be a0 by 2 plus summation n from 1 to infinite an cos nx, where a0 is 2 upon pi integration 0 to pi f of x dx, and an will be 2 upon pi integration 0 to pi fx cos nx dx, and bn will be equal to 0. So you have to remember one thing, that whenever a function is even and if the interval is given minus pi to pi, then bn will be equal to 0, and the formula for a0 and an will be equal to this. For a0 we have this formula and for an we have this formula, right? Then we have to substitute the value of a0 and an in this fx formula, so you will get the final answer. Next one, the Fourier series of an odd function in the interval minus pi to pi is given by the formula f of x is equals to summation n from 1 to infinite bn sin nx, where a0 equal to 0, an is also 0, and bn equals to 2 upon pi integration 0 to pi fx sin nx dx. Okay, now let's discuss one example. So find the Fourier series of function fx is equal to x square in the interval minus pi to pi, and hence deduce that pi square upon 12 is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square, and so on. So first thing, we have to see the interval. So interval is symmetric, minus pi to pi. So firstly we will check whether this function fx is equal to x square is even function or odd function, right? But we know, we have already discussed this function fx is equal to x square is even function. So whenever we have even function, the bn will be equal to 0. So what we need to find is a0 and an, and the Fourier series of an even function will be given by the formula f of x is equal to a0 by 2 plus summation n from 1 to infinite an cos nx. Okay, so let's discuss a0. So a0 is what? 2 upon pi integration 0 to pi f of x dx. Okay, so substitute the value of function fx. So here we have 2 upon pi integration 0 to pi x square dx. Integrate it, so you will get x cubed by 3, and the limit is 0 to pi. Substitute the limit and simplify, so you will get answer of a0 as 2 pi square upon 3. Okay, so this is the answer of a0. Now let's discuss an. So an is what? 2 upon pi integration 0 to pi fx cos nx dx. Substitute the value of fx, that is x square. Okay, now here we have to apply integration u dot v dx, Leibniz rule. So the formula is what? uv1 minus u dash v2 plus u double dash v3 and so on. Okay, here u is what? X square, and v is what? Cos nx. Okay, now let's apply this formula. So 2 upon pi as it is. Firstly, u we have to kept as it is, so x square as it is, and v1 means integration of cos nx. So integration of cos nx is what? Sin nx upon n minus here we have u dash, so derivative of u, so derivative of x square is 2x into v2 means we have to integrate this term. Okay, so on integration you will get minus cos nx. 1n is already present, so it will become n square. Next, plus we have to take derivative of 2x, that is 2, and the integration of minus cos nx upon n square, right? So integration of cos nx is what? Sin nx. Minus is kept as it is, n square is already present, so it will become n cube. Okay, and the limit is 0 to pi. Now apply the limit. So on applying the limit here, you know the value of sine n pi, that is 0. You know the value of cos n pi, right? And again sine n pi. So here just I have substitute the value. Sine n pi is 0. So first term is 0. Here minus minus will become plus. So here we have 2 pi into cos n pi upon n square. Again sine n pi is 0. So here we have 0 minus, now substitute the lower limit, right? So here 0, here also you will get 0, and again here sine 0 is 0. So this all terms are 0. Just simplify it, and the value of cos n pi is what? Minus 1 raised to n. So you will get the answer as 4 upon n square into cos n pi, that is minus 1 raised to n. So final answer of an is what? 4 upon n square minus 1 raised to n. Now we will substitute the value of a0 and an in the formula. F of x is equals to a0 by 2 plus summation n from 1 to infinite an cos n x. Okay, substitute the value of a0 and an. So you will get the final answer of f of x is equal to pi square upon 3 plus 4 I have taken outside, summation n from 1 to infinite minus 1 raised to n upon n square cos n x. Now we will discuss the proof. Okay, so the function was x square, so here I have written just x square, and we have to expand this. 4 is kept as it is. Firstly, substitute n is equal to 1 here, so you will get minus 1 upon 1 square, and here substitute n is equal to 1, so you will get cos x. Then for n is equal to 2, here we have 1 upon 2 square into cos 2x. Then for n is equal to 3, here we have minus 1 upon 3 square cos 3x, and so on. Okay, now we want the form like this: 1 upon 1 square, 1 upon 2 square, 1 upon 3 square. That is asked in question. So here we have to apply trial and error method. So firstly we will substitute x is equal to 0 and check whether we are getting the desired answer or not. So for x is equal to 0, so this function fx is equal to x square, so it will become 0. Pi square by 3 plus 4, everywhere cos 0, so it will become 1. So we have this term, right? Just simplify it, so you will get the desired answer which is asked in the question. Okay, so what we have discussed today: firstly, the interval was minus pi to pi. Okay, so firstly we have to check the interval, then we'll see the function. Okay, so if the function fx will be even function, then we have to find a0 and an, and the bn will become 0. And if the function fx is odd function, right, then a0 will be equal to 0, an will be equal to 0, and we have to find bn, right? And after finding this term, you have to substitute all the values in the formula f of x, right? So for even function f of x will be what? a0 by 2 plus summation n from 1 to infinite an cos nx, and for this here we will have f of x is equal to summation n from 1 to infinite bn sin nx. Okay, I hope you have understood this topic. Thank you for watching.